Welcome to our demo on OML-vect and compiler-assisted instruction fusion. This work was conducted as part of Static Analysis 5.3 deliverable, and in these demos we focus on general purpose RISC-V CPUs. First demo is on OML-vect. Here we propose two compiler passes to aid MLIR's auto-vectorization pass. The first step in OML-vect is to generate a ONNX graph using NSNet2 PyTorch model, and then we apply data layout modification, which will help the MLIR's auto vectorizer pass. And as you can see here, the maximal shape for weight matrix, the original shape was 257 cross 400. After we apply data layout modification, the shape was updated, and we also add a trans B metadata, which will aid the compiler in choosing a better algorithm which is suited for this data layout modification. And next step is to lower this into MLIR's affine dialect, and then we identify reduction operations. So the test match reduction pass is MLIR's reduction pass, which was not able to identify any reductions, whereas our OML pass was able to identify 16 reduction operations. This is because we identify complex reduction operations which MLIR's reduction pass fails to identify. Next step is to run MLR's auto vectorization pass, and after we vectorize, we further lower this to LLVM-IR and then to assembly and executable binaries. Let's run these executable binaries to get performance numbers. So here we can see that OML-vect was able to achieve 90% speed up over the baseline, whereas ONNX runtime was able to achieve around 89% of speed up over baseline. So with our modified data layout pass and a reduction pass, we will be able to better vectorize these algorithms for general purpose RISC-V CPUs. Thank you.
Hello, welcome everyone to the instruction fusion demo. We'll take the NSNet2 LLVM-IR generated from the ONNX MLR framework. We'll run some pre-processing passes like loop unrolling on top of the LLVM-IR. After this, we run the fusion passes. Fusion passes identify the fusible memory pairs, lay them next to each other for hardware to fuse. So the fusion pass could identify 63 fusible load pairs, two of which failed because of dependencies in between, and we could reorder 61 loads. For stores, we could identify 37 fusible stores, and all of them could be reordered for fusion. We use LLC to generate the assembly code for the baseline and the reordered versions, and we use linker to statically uh, to generate statically linked executable binaries for the baseline and the reordered versions. We compile the Linux kernel and boot the Linux kernel on top of RISC-V ISA simulator. The RISC-V ISA simulator helps us verify the correctness as well as generate traces for the CPU simulator. So here is how this takes a lot of time to run. So this is the execution log. So this is Linux being booted on top of ISA simulator, and this is where we run the NSNet2 binary. We only gather trace for the inference, and these are the predictions that we get after running the NSNet2. We compare these predictions between reordered version and the baseline to verify correctness. And yes, so the correctness has been verified and the traces have been generated. And, the generated traces are fed to in-house out-of-order fusion CPU simulator. So, and these are the logs that we get from the fusion simulator. So what is important for us is the Ruby cycles. So the Ruby cycles is the total cycles NSNet 2 took to run. So on the left is the baseline, on the right is the reordered versions. On the right, we see a clear reduction in the execution cycles. This is mainly because of increased fusion pairs. So from 2.1% to 29.87%. So so the execution time has been reduced by 37.4%. Thank you.